and welcome everyone. This is the Lynn Beazley AO Turn Ecosystem Observation webinar series, and it's great to have you all tuned in. Today, I'm talking to you from the Chapukai country in far north Queensland amongst the rainforest people. Feel free to put into the chat line where you're listening from. And to start today, and in keeping with the spirit of reconciliation, we at Turn acknowledge the traditional owners and custodians throughout Australia, New Zealand, and all countries. We honour their profound connections to land, water, biodiversity, and culture, and pay our respects to their elders, past, present, and emerging, and acknowledge the important role that Aboriginal and Torres Strait Islander people continue to play within our community. As I said, this is the Lynn Beazley Turn Ecosystem Observation webinar. We have Lynn joining us today. I don't know whether Lynn wants to say a quick hi before we go any further. Are you there, Lynn?
I absolutely am. Can you hear me? It's just wonderful. I'm so looking forward to this. Great speakers and how important. My gosh, a lot of extreme events right now.
Thank you, Lynn. And it's great to have you here today as we continue these wonderful webinars every second month. And Turn is really proud to host these. We're one of the Australian government funded research infrastructure groups, and you can see on the slide all the little marks on the map of Australia. We are well represented across the country, and we're very interested in extreme events as we collect data on everything. We have a lot of partners in Turn, and we always like to acknowledge them. They either fund us or fund us and help us operate, and also the community that makes use of all of the infrastructure that we use. Thank you, everyone. So today's event, extreme events, I should say, why do we need environmental data? We have three absolutely splendid speakers to join us. They're going to talk for about 15 minutes each, and then they're going to come together and answer questions that you may have put into the question and answer section or the chat of the Zoom section. I'm going to be really quite brief in my introductions of them because I really want to get into the content of the talk. And you do have their bios in your notes. But Dan Metcalfe, been on the advisory board of Turn for a few years now, and he is also the Director of Oceans and Atmosphere at CSIRO, formerly in Land and Water, so he's very well experienced in CSIRO. His current section has got over 500 staff around the country, and Dan's been leading the coordination of CSIRO science response to the 2019-20 bushfires and all the subsequent initiatives to improve resilience to climate-related natural hazards. He's also been coordinating the chapter of our state of environment related to extreme events, so he's very well qualified to talk to us today. Dan will be followed by Dr. Xihua, who's the Principal Research Scientist in the New South Wales Department of Planning, Industry and Environment. And Dr. Young's been doing something that we hope everyone does, and that is using Turn data. He's a long-time user of Turn data, and he has been using that to develop solutions to the after effects of extreme events, and he'll tell you more about that one shortly. And our last speaker of the day, Dr. Tim Wardlaw, is also somebody important to Turn. He's been the principal investigator at our Tasmanian Turn Warra Tall Eucalypt Super Site forever, since Turn started. He's also Turn's regional ambassador for Tasmania, and he has many different roles related to forests over time, and I'll let you read more about that. But now I'd actually like to get us going, and I'm going to stop sharing my screen and let Dan Metcalfe tell us more about his topic. Thank you, Dan.
Thank you, Beryl. And I'm just sharing my screen. which hopefully has popped up. So thank you very much. And yes, I'm Dan Metcalfe, and thank you to Turn for inviting me to talk today. And I'm going to provide an overarching view of extreme events from a national perspective before passing on to my colleagues for much more detailed treatment. To start with, I'd like to echo Beryl's acknowledgement of the traditional owners of the lands around Australia where we work. And I'm joining this webinar from Southeast Queensland, Brisbane, the traditional lands of the Jagera, Yugara and Turrbal people, the first scientists on this land. So what are we talking about when we refer to extreme events? The IPCC definition is that extreme events are weather or climate variables that fall near the ends of the range of observed values, whether at the upper or lower ends. And that's important because there isn't a specific line that you need to pass before it's extreme. And because particularly Australia, we only have about a century of meteorological observations, is the length of our observation mean that some of the more extreme events that are occurring naturally are either very rarely seen or perhaps haven't been experienced in recorded history. And also, as Beryl said, this is a distillation from some of the overview of the State of the Environment Report 2021 Extreme Events theme. So under the Environment Protection and Biodiversity Conservation Act 1999, the Environment Minister needs to table an independent written review of the state of the Australian environment to Parliament every 5 years. And this year is the first time that an extreme events cross-cutting theme has been written. And that's really in response both to a number of events in the last few years, but also increasing public concern about extreme events and their impacts. And I'd also like to note that for the first time, there is an Indigenous co-author appointed for every single chapter across the SOE, as well as an Indigenous co-chief author for the whole report, and an Indigenous cross-cutting theme as well. And I've been privileged to work with Oliver Costello, who's a Bundjalung man from northern New South Wales, and an expert in the application of traditional fire management to country. So Australia is a land of flood and fire. It's the driest continent, but parts of it exceed 4 meters of rainfall every year, and with highest rainfall records up to around 8 meters. And what we see is an environment that's evolved to cope with extreme events such that they're critical for ecosystem functioning in some areas. These big events stimulate a lot of groundwater recharge. Cyclones and east coast lows may deliver the surface water flows, which are often the only water that reach the arid interior of Australia. Coastal reshaping, particularly depositional events associated with storm surges and tsunamis, are really important for coastal systems. And extreme events, whether they're flood or fire or cyclones, are often the stimulus for reproduction or for the distribution of species. But whilst we have a short meteorological history and an understanding of the critical nature of extreme events, we're also beginning to see that those extremes are being measured with increasing frequency. Climate change is driving change to the weather, and over past decades, we've seen decline in rainfall in many parts of Australia, decreases in stream flow. We've seen increases in extreme fire weather, a decrease in tropical cyclones, and that's predicted to increase, but the decrease. So we're predicting an ongoing decrease in tropical cyclones, but particularly of lower category cyclones. And so what that infers is that the cyclones we see in the future are more likely to be more intense. We're seeing sea level rise, increased ocean acidification, and ocean warming. And what I'm going to do now is walk through a few examples of how climate change is driving change to the frequency, intensity, duration, and distribution of extreme events, and some of the consequences for us. So, for example, if we think about extreme fire weather days, then we're seeing increases between the 1950s, 1980s to the 1980s, 2020 period. Increases in drought and heat waves, together with lower humidity and great wind speeds, provide the conditions under which extreme fire weather days are likely to result in damaging bushfires if ignition occurs. We're already seeing, as I said, an increase in extreme fire weather days, and also an extension of the bushfire seasons. And dry lightning, which is a major cause of ignition, particularly in southern parts of Australia, is predicted to increase in the warmer seasons in southeastern Australia in coming decades. And so a consequence of increased fire weather days and the antecedent conditions that make it possible for fires to be particularly damaging resulted in unprecedented fires in the 2019-2020 season. And these were unprecedented because of the coincidence of fire across many states and territories at the same time, and an extremely long fire season with an early start and a late finish. And whilst many of you will be familiar with the impacts across southern and eastern Australia, Kangaroo Island, and into Western Australia, as this burnt extent map shows, there was also an extraordinary incidence and extent of fires across Cape York, the Top End, and the Kimberley. And I'll come back to data shortly, but it's worth pointing out that this national burnt extent map, which was generated to support the relief efforts early in 2020, was the result of integration of data collected from 11 national, regional, and state agencies. We also saw in this period an increase of smoke hazard and a high incidence of deaths attributable to smoke inhalation or complications arising from smoke. And we're seeing increasing incidence of bushfire-generated thunderstorms. Pyrocumulonimbus is generated as a result of the extreme energy released in bushfires. And these storms trigger unpredictable winds, lightning, hail and rain in their own sense. And those lightning events can stimulate or can trigger fires ahead of the existing bushfire fronts. While parts of Australia have become drier in the last 50 years, in other areas, the total rainfall has not decreased, but the rain is delivered in shorter and more intense falls. Increasing intensity of rainfall may exceed the capacity of catchments or urban stormwater systems to absorb or channel such rainfall, and this exacerbates flood risk in a non-linear fashion. Increased rainfall intensity over short periods may also mean decreased groundwater recharge, reducing inflows to water impoundments, and reducing longer-term water security. 2016 Tasmanian floods were a case in point. There was approximately double the monthly rainfall in the month of May. There was then a couple of days of very intense rainfall in June with rapid runoff, inundation, and flooding. A state government initiated review highlighted the role that preceding drought and bushfires played in increasing runoff, contamination of water supplies, and timber washing into river systems. Invasive species, particularly willows that had invaded river systems, contributed to debris dams and flooding, and changed land management and abandonment of some managed plantation systems also contributed to the impacts of that event. If we move to heat waves Heat waves occur by definition when both maximum and minimum temperatures are unusually hot over a 3-day period at a given location based on historical records. We've seen an increased duration and frequency of heat waves, both on land, but also in the water, in the oceans. And the hottest days have become hotter. On the right-hand side are some data from a Physical Environment Research Network review of potential impacts. And the 2030 RCP 4.5 data suggest some quite dramatic increases in the number of heat wave days in various capital cities across the country. So RCP 4.5 is an intermediate climate change scenario, which would deliver a global warming of about 1.5 degrees by 2050. So that's pretty much where we're sitting at the moment. And whilst those are consequent, whilst those data have been generated for understanding the impacts on our cities, we also see direct consequences for people, agriculture, and the environment, and indirect consequences through impact on water availability, season, and vegetation drying. The combination of very hot days followed by hot nights means that people and native biodiversity have less chance to recover before the high temperatures of the following day. And in recent events, we've seen the susceptibility of native animals to heat waves, with heat stress responsible for the deaths of thousands of flying foxes across several species and several states in recent years, and particular concern for small arid zone birds, which are at particular risk because they already occupy habitat where they're living close to their physiological limits, and heat waves can cause loss of condition, abandonment of nests, and increased mortality. Forecasting also suggests that current climate zones and weather event types are likely to shift, which may challenge species and ecosystems to either move with those changes or to face different environmental and phenological challenges. And buildings and our infrastructure in our own created environments are also at risk. And an example here is severe tropical cyclone Xihua, which impacted the West Australian coast earlier this year. This is of note because this is the first cyclone to have crossed the coast at around this point since 1956. And yet the building codes on which standards are developed were instigated on research begun in the 1970s. And so in those B category wind regions, we saw lower minimum building standards, but also some low maintenance thresholds and adherence to standards, which had the consequence of massive damage to buildings and infrastructure. And the last data I saw suggested in excess of $25 million in insurance losses. And so forecasts, some modeling suggests that cyclones may track further south than we've seen before, or at least they may more frequently track south. And so that has impacts both on our cities and our infrastructure, but also on natural systems which are particularly impacted by cyclones. And so where does data come in? So forecasts are built from models, and models need data to train and improve them. TURN and other entities funded under the National Collaborative Research Infrastructure Strategy, NCRIS, are already providing critical data to support this. National initiatives such as the Australian Climate Service will pull data from across sectors to provide authoritative information to policy and decision makers and operational agencies going forwards. Generating environmental baselines to understand how change is wrought and potentially the establishment of sentinel sites where we think we're likely to see change so that we can be made aware of changes early in their onset is also of value, as is developing a quicker and more coordinated response to events so that we're able to get into impacted areas and understand their impact, the consequences for the environment early on. And part of that is reaching out to citizen scientists and a growing recognition of the value of harnessing the enthusiasm and the technology, as well as the insights of people living in areas that are impacted by extreme events, and the capacity that they have to collect data in an formerly unprecedented manner. And finally, common minimum metadata standards and national platforms for the collation, integration, processing, and delivery of data are critical going forward, so that rather than spending months integrating, for example, the 11 data sets that were needed to build a national bushfire extent map, we can press a button and download those data in near real time, and so provide faster and more authoritative data to operational agencies and managers. I'm going to stop at that point. Thank you very much for listening. Next presenter is Dr. Xihua Yong from New South Wales Department of Planning, Industry and Environment. Thank you very much.
Thanks, Dan. I would like to acknowledge I'm here today on the land of Darug people. The Darug people are the traditional owner of this land. I also acknowledge the present Aboriginal people who now reside within this area. Good afternoon, everyone. My talk today is on the rapid assessment of post-fire erosion with a case study in the Sydney drinking water catchments. It is a collaborative project with Water New South Wales. So here I'd like to acknowledge my collaborators from Water New South Wales, also my former PhD students from UTS, and the collaboration from Griffith University, CSIRO, and my DePaul colleges. The Sydney drinking water catchments is one of the large water supply in Australia. It supplies water, drinking water to about 5 million people in Sydney and the surrounding regions. The Black Summer Fire in 1919 and 2020 burned about 80% areas in the Warragamba catchment special regions. So this caused a greater concern of erosion and the water quality. So this need timely information of erosion and sedimentation for water quality management. So in collaboration with Water New South Wales, we developed a rapid assessment method to estimate the erosion after bushfire, especially after storm events. We used a widely used model. It's called Revised Universal Soil Loss Equation, or RUSSEL. The model considers 4 factors: topographic, or LS factor, that represents the landscape impact on the erosion in terms of slope, slope lengths, and the shapes. The second factor is the soil erodibility factor, or K factor, that represents the soil properties such as soil texture, organic matter, permeability, and structure, the impacts on soil erosion. The third factor is cover and management factor, or C factor. That is the ground cover protection to soil erosion. In events of bushfire, we also need to consider the fire severity. The fourth factor is the rainfall erosivity factor. That's the rainfall impact on the erosion and runoff. That's the most dynamic factor. Among them, LS and the K factors, they are reasonably static. Cover factor change seasonally or monthly. The rainfall is the most dynamic factor. So for the erosion modeling, we need to use a lot of data sets, such as rainfall, the vegetation cover, digital elevation model, digital soil maps, and a range of satellite images. Also, we need to use fire severity and the field data. Most of the data are available from TEN. We use the digital elevation model to estimate the slope lines factor based on the Russell guideline. We produce the statewide LS factor map from the centimeter DEM. Then we use the digital soil maps from TEN to estimate the soil erodibility K factor based on the Russell normal graph methods. Then we produce the statewide soil erodibility map. For the cover and the management factor, we use the monthly fractional vegetation cover from Moody's, also derived from Landsat and Centennial, based on the relationship between the total cover and the C factor or bare ground. Then we produce the monthly time series of the C factor since 2000. Then we developed a so-called daily rainfall erosivity model to estimate the monthly rainfall erosivity. This has been applied for the entire state of New South Wales on monthly basis. We have the rainfall erosivity estimation for over 100 years. Then this is an example of the monthly time series of the soil erosion. We have this amount for 20 years. So based on the time series, we can estimate the erosion risk at any location and at any time across the state of New South Wales. So that's the monthly average erosion rate, and then that's the erosion at New South Wales land surface regions. For the scenic drinking water catchments, based on the monthly estimation, we can find the post-fire erosion in February 2020 were extremely higher. It was about 30 times higher than the average erosion rates in February. That's because of the prolonged drought period and the fire. Also, the February storm is very intense. We estimated it's over like 1 in 40 years. So based on the monthly erosion modeling, we can only estimate the monthly erosion rate, but it is not enough for storm-based erosion, because for water quality monitoring, we need the erosion modeling at a much higher temporal resolution. So that's why we use the weather radar data. It has 10 minutes temporal resolution. That means every 10 minutes we have an image. Then we can use this data, or this spatial resolution is 1 kilometer. We can use this data to estimate the rainfall erosivity, or called EI30. That means in every 30 minutes, what's the rainfall erosivity? So we can use this data to estimate much short storm period. Then based on that, we can estimate daily or even hourly erosion. So here is the estimation of the post-fire erosion in city drinking water catchments. That's in February. You can see the erosion only caused by a short and intense storm events. In this case, it's around 9th February 2020. So the daily erosion counts for 65% of the monthly erosion. Also, if you can see the hourly erosion, so on the 9th of February, the erosion only concentrated between 12 and 6 p.m. So with the weather radar data, we can estimate basically the erosion on storm basis. So that's much useful for water quality monitoring. So that's an example of the erosion rate before and after the fire in city drinking water catchments. So with the timely information, Water New South Wales is successfully maintained the water quality by preventing the inflows from a high erosion area into the goes into the lake. We also developed tools, use GOGAS engine and the GIS, so we were able to quickly estimate the erosion risk after storm events. As I mentioned, because most of the data already available, most of them available from 10, so this technology can be applied in other areas. We also have some future prediction using the NACNAM data. That's the New South Wales and the ACT regional climate model. So based on the NACNAM prediction, we predict the future change in rainfall erosivity and erosion. We predict the rainfall erosivity is likely to increase about 6% in the next 20 years, but increase about 19% in the far future or in next 60 years. That's because due to the more extreme rainfall events. For your information, now the NACNAM 2 is under development. It's probably going to be available maybe in a couple of years. With the NACNAM data, we also estimated the change, the future change, the seasonal change. We can see the rainfall erosivity and the erosion change in different seasons. We found in autumn and the summer, they increase more in the future. So currently, our model has been extended to the entire nation of Australia. We have already produced the slope steepness factor in 90 meters from the arc 1 second DM is roughly about 30 meters. But for nationwide, the final product is 90 meters. We also produce the soil erodibility factor, K factor, in 90 meters from the digital soil maps available from 10. Then we have the MODIS derived monthly fractional vegetation cover. Then from CSRO. Also, we have the monthly or daily rainfall from Bureau of Meteorology. So we use all this data to produce the time series of rainfall erosivity and erosion for the entire nation of Australia. These erosion products are available from a state for New South Wales monthly and annual data, adapt New South Wales for the future projection, and for national data are available from a CSRO data access portal. I think that's all for my presentation. Thank you for listening. Now I'd like to hand over to Dr. Tim. Tim, over you.
Okay, Xihua. I'm hoping my screen will start sharing anytime soon. So thank you, everyone. I'm hoping I can't see what my screen is sharing, but I'm assuming it is.
On, Tim.
As Beryl said, I've been around forever with Tern, so which is just as well because the story I'm about to tell you is 120 years in preparation. So the last fire we had at Warra was in 1898. We do fires slightly differently in Tasmania. We don't have the large, intense stand replacing fires typical of southeastern Australia. We have a much more benign beastie, but they're also a very rare beastie. We didn't know much about them. So the story I'm about to tell you started in the 15th of January in 2019. We had a dry lightning storm, a couple of storms passing across southern Tasmania, something over 2,000 lightning strikes, and that ignited 70 fires in quite remote areas of southern Tasmania. And some of those coalesced to burn around about 60,000 hectares of tall wet forest in and around Warra in the Xihua Valley. You can see the extent of that fire here in the brown shaded area. Warra, the long-term research site, is the Cross Hatch area, so that covered quite the central extent of the fire. And we have a number of Tern facilities within the burnt area, including the flux tower, the 80-metre tower in the forest, and 4 1-hectare plots, one associated with the flux tower and 3 others, which are a part of the Tern surveillance facility. And we've measured the conditions from the flux tower during the passage of that fire. You can see in the bottom graph, looking at soil moisture, this is coming from the Bureau of Meteorology's climate station at Warra. As you can see, leading up to the fire in December, there was a lot of rainfall events, so the soils were quite moist coming into January, and then they progressively dried. And during the passage of the fire, the main period of the fire, we didn't see much integration or high rain, high temperature, low humidity and high winds coinciding to lead to high fire danger rating. So there were really only 4 events through that whole period. We had the dry lightning storm, we had an increase in fire danger index at the bottom. On the 21st of January, we had quite a spike there with winds and humidity dropping, winds increasing, and that's for the Reveau Road fire, broke containments and rapidly spread. The day before Australia Day, we had, again, a spike in the fire danger index, and the Clearwater Creek fire, which was just upstream from the flux tower, jumped the Xihua River about 1 kilometre west of the flux site. And then on the 28th of January, we saw again the temperatures picked up and the winds picked up, and that's when the fire burned through the flux site. But generally speaking, the fire danger index for most of the time was relatively benign and really was in the moderate range for most of the time. So it's not the extreme fire danger. This is just the fires that burned through the site. This is recorded. So the left-hand graph, the photograph is from the fender cam at the top of the tower. So you can see it was very smoky. I was glad I was not down there today. The air temperature, this was measured at a profiling system on the side of the tower, at 16 metres. We saw a spike when it got up to 70 degrees, and then it fell down very, very quickly afterwards to about 50 degrees, late in the afternoon on the 28th. And you can see on the right-hand graph, the cumulative release of CO2 measured by the Eddy Cavarian system. You can see release of CO2 building up through the day and spiking in the afternoon, in late afternoon as the fire went through. It stopped at a bit after 5 o'clock when the fire burnt through one of our electrical cables and shorted everything out. We had cameras taking photographs before and after using the photo points in the 1 hectare plot. This is what it looked like before. And after, you can see the fire consumed all the litter and ground vegetation and scorched the understory trees and shrubs. Now, in November, prior to the fire, we had mapped and measured all trees greater than 10 centimetres in the 1 hectare plot adjacent to the flux tower. In November, 6 months after the fire, we remeasured that with the assistance of the Adelaide University surveillance crew to look at what effect the fire had on the status of the forest. Just looking at survival, we found that most of the eucalypts and the man ferns survived, but very few of the understory trees and shrubs did. So you see a large drop in survival, large mortality of blackwood and understory shrubs like the Rhodophagus and Pomaderus, all very low survivorship. Man ferns were quite bizarre. Most of them, the fire had burnt them off at ground level, so they'd fallen over. Some had even moved from their map position when floods came through after the fire and dislodged them further downstream. Despite that large loss of trees in the understory, most of the carbon that was in the standing live trees prior to the fire was still in the standing live trees after the fire. And that was because most of the carbon is contained in the eucalypts. About 80% of the above ground carbon is in the eucalypts. So the fire had very little effect on carbon storage in the forest. So that 10 tonnes per hectare that was released, we measured in the flux, with the flux equipment, was pretty consistent with the amount of biomass that was lying on the floor that had been measured by Jamie Furlow and others prior to the fire. So whilst it was a ground fire, it was still hot enough to scorch some of the leaves in the understory and the overstory. You can see here the aerial view from the flux tower. You can see quite a bit of scorch surrounding the flux tower. It tends to be along access lines where we get a bit of build up of wind speed, so it's like increase the fire intensity. And that resulted in a decline in leaf area index that we measured in the 1 hectare plot. There was about a 30%, or a bit over 30% decline in leaf area index, and that was concentrated mainly in the lower mid strata, surprisingly. And this is we've had time series, and you can see the drop this is the average of nearly 6 prior to the fire, dropped down to about 4 after the fire, and has not been much recovery since that time. We've been measuring that every 6 months and not seen much recovery yet. I haven't been the only one getting ready for the fire. The eucalypts were doing that too. So 2 years before the fire, this is what we captured with the Benecams on top of the tower, a heavy flowering event in the Obliqua in February 2017. And the seed from that flowering event would have been optimal maturity by the time the fire went through in January 2019. And we saw that with seedling surveys we did soon after the fire. We recorded, this is surveys we did not just in the core 1 hectare plot at the super site, but in the three other turned 1 hectare plots as part of the Ausplots forest network. And using point intersect sampling, we recorded over 114,000 acacia seedlings per hectare. They're a ground stored seed. About 45,000 eucalypts per hectare, about 44,000 Pomaderus per hectare. So Pomaderus and acacia both have ground stored seeds, so they would have had large soil seed banks. The eucalypts benefited from the heavy flowering event 2 years previously. So something like a bit over 200,000 seedlings per hectare of those three species, about another 150,000 seedlings per hectare of other species we couldn't identify. So across the 30,000 hectares of the wet eucalypt forest that was burnt in the 2019 fire, something like, if you extrapolate those numbers, something like 6 billion seedlings were sown by nature. So they did a pretty good job in meeting the Commonwealth Government's objective of 1 billion trees, the burnt areas. Looking at the recovery of carbon fluxes, so before the fire, this is a plot of the cumulative carbon uptake by the, or released by the forest in the period 1st of December to 31st of December, 1st of September to 31st of December, sorry. You can see prior to the fire, the orange, the blue, orange and grey lines, you see a steady accumulation of carbon, sequestering, uptake of carbon around about between 5 and 10 tonnes per hectare in that period. In the first year after the fire, 2019, you saw the forest switching from a carbon sink to a carbon source. Now, 2020, the second year after that, we started to see what appeared to be a recovery and then drop. So I suspect what's going on there is it was a very cold spring in 2020 and the ideal conditions for productivity of warra. And then the temperatures picked up a bit towards the end of that growing season. That's when we saw that big drop. So it's showing that the forest has still got some work to do to recover to what it was before the fire, but it's working towards that. Now, so what we've learned, we didn't set out to learn other than tell the story here. This was just purely opportunistic, but what we did learn was the suite of core measurements we make at the super sites are able to describe the key attributes of that rare disturbance event. So we learned that extensive fires can burn in those tall forests with fire where the conditions are relatively benign. We learned ground fires, by causing little damage to the overstory, a standard place into the understory. So very, very different effects on by strata. We learned that most of the carbon, live tree carbon, remains after fire, but we also learned that the forest switches to a sink after fire, and that's not unexpected. What we have still to learn is the fate of the regenerating seedlings, and particularly the eucalypts, because don't forget the seedlings are regenerating under an intact canopy. So we would expect that most of those eucalypt seedlings would not continue to grow into the future, but we haven't got many points to say that. Because of that, we don't know when the forest is going to return to a carbon sink again. So we had carbon gains from regenerating seedlings, perhaps, the surviving eucalypts, but will they compensate for the losses through decomposition of the understory? And that's about 200 tonnes per hectare of the rainforest trees that are going to decompose. So that's the story. It was a big team. Alison, my supporter from Forestry Sustainable Timbers TAS on the site, great work done of the incident management team of the Revo Fire, keeping Warra Tower standing, and Comstar, Hewitt Communications and Gandy and Roberts for the restoration of the tower after the fire. Adelaide University surveillance team for helping remeasuring the plots. And then Ken Stronach and Melita Hinkling from Tohoon Adventures for their support in developing this story as part of their interpretation. Now, we're on extreme events. I'll finish up with this. This is a shock. This appeared when I visited Warra last week to find our tower had collapsed. So it was brought down on the 23rd of September. We had a severe storm pass through. This was the day after the earthquake in Victoria. The week leading up to this, we had very heavy rainfall right through Warra, so the grounds were wet. And then we had this really intense storm come through with, you can see the wind speeds there, and the 5.5 hours leading up to the collapse of the falling of the tree in the tower. We have a lot of spikes above 80 kilometres per hour. So it was a very intense windstorm. So that's my story. I'll now stop sharing my screen and hand over to Beryl.
Thanks, Tim. that was actually extreme events in action, I think, to hear so much. And I think you had droughts at some point before that. So you've had drought, fire, wind, earthquake, heavy rain. It puts it
And
all,
heat wave.
and a heat wave, that's right. So we've done very well there. And perhaps if all of our panelists can now switch on their cameras so we can take some questions from our audience. And while they're just doing that, I forgot to mention a little earlier that this has been a fantastic rollout for this webinar with over 200 registrants from many different countries and across Australia, from all sorts of different agencies and just individuals involved. So it's a topic that's of great interest to everyone. Xihua, can you put your camera on at all?
It says stopped.
Maybe Marianne can fix that one for you.
Yeah, it says host has stopped it.
We will just.
Oh yeah, no, okay.
Yep, all back together again. So I'm actually I'm just going to head off with a question that occurred to me. That's really, first of all, for both Dan and Tim. So Dan, your talk really highlighted that extreme events are getting more regular, and that our environments may not be able to recover from such regularity. So resilience becomes quite a major factor. And then Tim, in your talk, you showed us the incredible seed beds that are around Warra. And whilst we have no knowledge as to whether extreme events like the fire will get repeated, since it was 120 years between major fires there, but if another fire came through this season, presumably the seed beds would be depleted. And this is what you were talking about, wasn't it, Dan? So I'll let you two just talk with microphones.
Yeah, thanks, Beryl. As I said at the beginning, extreme events are critical for ecosystem functioning, but many species and communities have evolved to a particular suite and a particular frequency of extreme events. And so what we're seeing under the current climate change is a change in frequency distribution, duration and frequency of events. And so to simplify it, you might say that the extreme events are getting more extreme. And so the real concern there is, whilst they're fundamental to some ecosystem processes, is that are we entering a territory where the events actually become too extreme for species to respond to? And so I suppose there, as you say, for Tim's system, is if fire returned through those systems before those seed beds had a chance to reach maturity, are we looking at ecosystem changing events rather than kind of natural dynamics? Tim?
Yeah, it's an interesting one, how to just predict how ecosystems might evolve to become more resilient to the extreme event. The system at Warra is the eucalypts, for example, are quite resilient in that most of the eucalypts have resprouted from epicaumics after the fire. So there's been very little mortality in the eucalypts and the ferns, but the fate of the understory is something I don't know how much of the soil seed store was depleted. I think this is pretty typical of the sort of thing you're talking about, Dan, is very typical of what we've seen happening on the mainland, where particularly in the Delegatensis forest, where there are forests south of Canberra that have suffered a sequence of fires at much greater regularity than they would normally be used to. And those Delegatensis forests there aren't epicaumic producing, so they're not resprouting ones. So I think there's work to look at getting epicaumic, Delegatensis have got an epicaumic ability to help recolonize some of the, or keep Delegatensis in some of these forests. So I guess that's part of the things we have to think about in terms of making some of these systems more resilient.
Thanks, Tim. I'm going to, there are some nice questions sitting in the Q&A, but I'll let everyone have a read of that. I've got some thoughts on that, but I want to ask Xihua a question that has come in. So incredible work on hillside erosion mitigation. What's in your work pile next to help people with post-extreme event? Are you working on something new?
It's not it's not totally new, because we did the hill slope, did the sort of erosion modeling. In the future, we need to do how the sedimentation goes to the lake, goes to the drinking water system. So we need to do some sort of transport and the pollution modeling. So to predict how much sedimentation and the pollutant materials goes to the river, goes to the lake. So that's one of the things we are trying to do. Also, Will asked a question, so how we do the in situ sort of measurements. So in the future, we're going to have more soil trips, like plots, to do some sort of measurements to validate our model. So that's the other thing. Because of the pandemic, we already planned the field work, so we were unable to go. Probably once the restriction is over, we go to do some more field work.
Thank you for that one. And I can see that answers are being typed into the Q&A. We are recording this session, and I think the Q&A session goes with the recording, which is really good. The last one that's come into there from South Africa addresses a problem we're having right across all our observatories, I think, continental scale observatories, and that is, with extreme events, do we take it on the chin every time something comes through and destroys our infrastructure, or is there something that we can do to help that one? We're working on that one very much. We're looking at a lot more mobile platforms that can be more agile and pulled out, put back in, but it doesn't, in some places you just need the 80-metre and 75-metre towers. That's things that were burnt out in the last round of bushfires. And did anyone want to add anything to that? I know you're typing answers.
I thought, so one thing, it was very, I think in terms of resilience, having cooperation, it was the team effort we had with the incident management team, it was great for the Warra fire. I don't know what we could have done with the fire that Tumbarumba had, for example. There were some fires you've just got to walk away from and go to a church and pray, I think. But in terms of preparing for the site, trees coming down over guy lines we know are always going to be a problem. And if we can find ways of funding non-guide towers, freestanding towers, that would be clearly the way forward.
But Tim, I think that you said in your talk that there's no replacing the unique and rare information you can get from having your infrastructure right bang in the middle of an extreme event, collecting data that no one else would otherwise collect. So maybe sometimes we just need to make sure that the instruments keep going while the event is on. That's the answer. And oh yes, Dan.
Yeah, thanks, Beryl. So I think that it's happenstance that we have instruments in situ when an event happens. But I think the kind of work that Turn's done in generating baselines across the country and understanding what systems look like mean that even if we don't have an instrument there, we have the capacity to go back and see really quickly how things have changed. We do occasionally have instruments in place. There was a sail drone that got in the middle of a typhoon off North America recently, which gave some fantastic data. But again, it's luck, it's happenstance that you're actually there at the right time. So I think in a terrestrial system, the more we can build our understanding of what systems look like, so that if we aren't actually there at the time, we can respond really quickly. That helps. But the other point I made was about citizen science, and so the work that's been done on Kangaroo Island or the observations of the hailstorms in 2019 in Brisbane are really examples of, if you're not there measuring hail when it hits the ground, it's too late. And so we have, I think there were 242 reports from that individual storm. And that's generating a massively enriched understanding of those kind of events. So it's not just the infrastructure, it's having the people there and using the people who are there.
Thank you very much. I'm going to wrap up now, as it is the end of our time. And while I'm just saying a few words, I'll flick up the topic of our last webinar that will be happening for the year. But I'd like to thank each of our speakers. Dan, you've shown us that extreme weather events are important for ecosystem functioning, but they're likely to become more extreme in the decades ahead with all sorts of consequences. Xihua, you've helped us understand that you can be very positive and with data and extreme events by coming up with a rapid assessment for post-fire erosion, so that we can get timely recovery and mitigative actions. And Tim, making detailed measurements of a fire in a forest that last occurred in 120 years ago, not something you can plan for, as Dan said so nicely, happenstance. So thank you to our audience for a fantastic set of questions and for joining us today. And thank you once again to our speakers. And we'll see you all in December. Thank you.